Okay, we'll see if we can get through this with one take. What we're going to demonstrate is the General Radio Model 1603A ZY bridge. This was introduced in 1962, designed primarily by a very good engineer, Ivan Eastham at GR in Concord. And its claim to fame is it can measure from 0 to infinity of anything, reactance, resistance, what have you. That's a pretty tall claim. Yeah. Well, the reality is it can do that, but measuring 0 to great precision with this is just not in the cards. It does okay at 10 ohms. Measuring infinity with this, it's just not in the cards either. You need a specialized piece of gear to measure infinity. It's a wild claim, but there's some truth. It is true that it will develop a balance at either 0 or infinity, because it can measure either impedance, Z, or admittance, Y, 1 over Z. Okay, so let's cut to the chase here. How do you run it? Well, it needs an oscillator, a generator for a signal, and it needs a detector, just like all bridges. And these are the unknown terminals here. I'm using an HP 3551A transmission test set that I just happened to be messing with the other day, and I said, this thing can be useful. It's a combination of a signal source, a sine wave, that can go from 40 hertz to 60 kilohertz, and a sensitive detector that reads out in decibels, which is a very handy thing when you're looking for deep nulls, okay? So we've got the source connected to this gray lead here. This is the send end of this device, this test set. And we've got the detector going into the receive end of this device, okay? So we've got our source and our detector, and we can read out, in this device, we can set frequency. So I've got it set to 1 kilohertz. You can vary the frequency over the range of the instrument. And this is on the send end. And now I go over here to the receive side, and I look at level. And it's minus 24.9 dBm. The absolute value doesn't matter. It's all relative. All right, so the first thing you have to do with this bridge is develop an initial balance. So I'm going to measure impedance to start with. You never know. You have to understand your unknown a bit, but let's start with measuring impedance, and I've got it set to normal. I'm not going to go into what reversed means. It's going to take too long. But normal is normal. All right, so Z initial balance is set to normal. Then you take these two controls and you tune for a null over here. Now, we're going to tune these two, and it doesn't matter what these are set to. You tune this, see if I can. See if we have the demonstration effect. You'll hear some clicks because this guy auto ranges in 10 dB steps. So we're getting down there, minus 58. Oh, I saw a minus 60 breeze by there. The better you can set this initial balance, the more accurate your result will be. Okay, so we're at minus 65. That's really good. Okay, then we have to connect the unknown, and we'll go to Z measure. So here's Z measure, and as you can see, we were at minus 65. Now we're at plus 15. It's like 80 dB change. We're going to start with something simple, the unit short. So we have a couple of clip leads, yes, and a kilohertz. It doesn't matter too much. We're not looking for milliohms here. All right, so we've got the short. And, okay, not bad, minus 16.6. No, we're going to have to tune it. So here we set in this mode, this is the resistance balance setting, and this is the imaginary part, the X, if you will, in reactance. Z equals R plus JX, and I'm looking at minus 42, minus 39, minus 50, oh boy, I saw 56 go by. These are wire wound pots, by the way, in the instrument. So, you have a one wire quantization here. And it's very fine, but okay, we're at minus 55. I'm going to settle for that. So the question is, what should we be reading? The answer is 0. So let's have a closer look. Here's our X dial. I can see that you can see that's 0. And here's our R, as in real part dial. And you can see that that's 0. Congratulations, we've measured 0. Now, next thing, an unknown. Start simple, add detail. Always know the answer before you ask the question. We'll start with a known resistor of 499 ohms. Actually, it's, 497 ohms is really what it is. All right, I'm going to dangle it up here to get it out of the way. It's not easy. Hello. Oh, that's awful. Okay, there we go. Maybe. All right, minus 2.2 here. We're going to tune the R dial. All right, we're down at minus 50. Minus 52. I'll tweak the X. It should be 0, or close to it. Yeah, I got a little better. Okay, so there we are. Here are our readings, okay? Here's our reactive part. Well, it's 0 for all practical reading purposes. And here's the real part. And the real part is just shy of 500. Remember, the right answer is 497. So congratulations, we have measured a resistor. All right, next up, we're going to measure a capacitor. Again, you have to know the answer before you ask the question. So this capacitor is marked as 0.334. Hello. Well, that ain't working well, is it? Oh, I give up. Yeah, you can see 334 on the bottom, vaguely. The light's not good. All right, that's 0.334 microfarads. The actual value is 0.3255 microfarads. How do I know that? Another bridge. Oh, and we're operating at a kilohertz here. This operates between 20 hertz and 20 kilohertz. It covers the whole audio range. To keep our life simple, we're running at a kilohertz. All right, so here is my capacitor. Oh, is this fun or what? All right, now, this shouldn't have much of a real component, so I'm going to set that to roughly 0. And then I'm going to tune the imaginary component. And if you watch this, you'll see it diminishing. And we have to now do the fine tuning. Minus 40. A little tweaking here. Minus 50. Minus 62. I'm going to stop there. That's about as good as you can make it. It's within a wire. Okay, so let's have a close look. Here's the reactive part. And as you can see, it's basically 500. Okay? 500. And here's the real part. A little bit above zero. What's a little bit? 8 ohms, maybe? A very reasonable number. Q is ratio, so, the Q is pretty high. It's not infinity. It's quite a decent result. Now, what should the reactive part be? Well, it should be 489 ohms, minus 489 ohms. If you recall, it was 500. So we're very close. Now, here's the next trick. We're going to measure the series combination of the capacitor and resistor. Now, I shouldn't really have to change this dial over here. I shouldn't have to change the reactive part. Shouldn't be the key word. I should have to change the real part. And it ought to come out to be 500, or real close. Okay? And here we are at minus 64 over here. And let's look at the results. Oh, we have 500 and 500. Absolutely wonderful. Congratulations, you've measured the series combination of a capacitor and a resistor. So, I could go on, but I'm not going to. Bottom line is, it's a very interesting bridge because of the ranges it covers, and it does cover 20 hertz to 20 kilohertz, and it does require, a generator and a detector. And this little HP transmission test set does a nice job of doing that. So that's it from the Bat Cave. Carry on, and happy measuring.